Okay, so to get a sense of these reciprocal functions, okay, and as I just mentioned, when we look at something like, let me get the pen working, y equals f of x, and y equals 1 over f of x, these two functions are called reciprocal functions, okay? Okay. In 20-1, f of x will always be a polynomial function, although it doesn't have to be, okay? Okay? All right, so to kind of get a sense of what's going to happen with these reciprocal functions, we're going to do a comparison, because what we're going to see is that if we know what the graph of f of x looks like, and we've looked at graphs of polynomial functions, particularly graphs of linear functions and graphs of quadratic functions, okay? If we know what f of x looks like, what we're going to learn today is that we can actually tell what the reciprocal function looks like as well. Okay, but we're going to explore that a little bit. So to do so, we're going to compare y equals x, okay, so that's our f of x, to its reciprocal. So here f of x would be x, right? Or we could say that, actually a better way of putting it would be y equals x. And this one would be y equals 1 over x. Okay, and to do so, we're just going to make a table of values. Okay, so first one is a very simple linear function. If x is -3, y equals x, y is going to be -3. If x is -2, y will be -2. When x is -1, y will be -1, and so on and so forth. Okay? Now, when we look at the reciprocal, y equals 1 over x, when x is -3, y is going to be 1 over -3. Okay, when y is -2, f of x is going to be 1 over -2. This is going to be 1 over -1. This would be 1 over 0. What happens there? 1 divided by 0. Yeah. 1 divided by 0. Can you take like one cookie and divide it into 0 parts? No, yeah, it's undefined. Right? And if I had the expression, the rational expression 1 over x, the non-permissible value there would be that x cannot equal 0. Okay? So we're going to actually look at what happens there, but we are not actually going to have a y value there. Okay? This would be 1 over 1. This is going to be 1 over 2. This is going to be 1 over 3. Now, what I'd actually like to do as well is add some additional values to look at that are not in here. I'd like to add in x equals -1/2 and 1/2, and -1/4 and 1/4. Okay? So firstly, if we look at the y equals x situation, when x is -1/2, y is -1/2. Right? When x is 1/2, y is 1/2. When x is -1/4, y is -1/4. And when x is 1/4, y is 1/4. Okay? Now when we take y equals 1 over x though, if x is negative a half, this is going to be 1 over negative a half. Okay, this is going to be 1 over a half. This is going to be 1 over negative a quarter. And this will be 1 over a quarter. Okay. Now, forget about the negative for now. Actually, let's just look at this one. 1 divided by a half. If you divide 1 into halves, how many halves do you have? 2. Yeah, so this is equal to 2. That means this is negative 2. Okay, if you divide 1 divided by a quarter, how many quarters do you have in 1? You've got 4 quarters, so this is 4. This one would be negative 4. Okay, so we're going to plot these. So the first one, y equals x, I mean, that's a linear function. So that's not too bad to plot, right? The y-intercept is 0. The rise over 1 is 1 over 1. Or you could just plot these points. When x is negative 3, y is negative 3. There we go. When x is negative 2, y is negative 2, and so on and so forth. 0, 0. Right? There we go. There's the linear function. Okay, so I got to do this straight on. There we go. Okay. Now, this other guy, though, I think I'm going to do this in a different color. Maybe I'll do this in red. Okay. Well, when x is negative 3, y is negative a third. So when x is negative 3, y is about there. Okay. When x is negative 2, y is negative a half. That's about there. Oh, wait, I messed up. My x values are wrong. Okay, let me erase those. That's better. All right. Let me fix this. Okay, negative 3. 1, 2, 3. When x is negative 3, y is negative a third. There we go. When x is negative 2, y is negative a half. When x is negative 1, y is negative 1. Okay, now let's go to the next one. When x is negative a half, y is negative 2. So over here, y is down here. And when x is negative a quarter, y is negative 4. There we go. Okay. And then when we plot the rest of these, okay, when x is 0, y is undefined. So we'll see what happens there in a sec. When x is 1, y is 1 over 1, which is just 1. Okay. When x is 2, y is a half. So that's here. When x is 3, y is a third. Okay, and then I also did these ones. When x is a half, y is 2. And when x is a quarter, y is 4. Okay, so if we see what's happening here, it looks like there's a curve that's going like this. And there's another curve that's going like this. That is the reciprocal function. Okay? Now, what I'd like to talk about is firstly this sort of vertical line, which is in fact the line x equals 0. X equals 0, by the way, was the non-permissible value. Okay? Now on the graph, that's actually a vertical line. Okay, so that is, I'll switch to green maybe, this guy. This line is x equals 0. And also this horizontal line over here, which is the y-axis. And that is the horizontal line y equals 0. Okay, now these two lines have special names. They are kind of funny names. They're called asymptotes. Okay, and an asymptote is a line that a curve gets very, very, very close to, infinitely close to, but never actually touches. Okay, an asymptote can be a vertical line or a horizontal line, or it actually can be a slanted line as well. If you take AP Calculus, you will look at slanted asymptotes, or if you take calculus in university, you'll also look at slanted asymptotes, but otherwise you're only going to look at vertical or horizontal asymptotes. Yeah? You don't have this? What? Okay, hold on. Oh. Oh, you don't. Okay, I'll write it out again. Yeah, I can erase this. Because you guys all have this down, right? Okay. Yeah. Okay, so an asymptote is a line that a curve gets very, very, very close to, but never touches. Okay, and we're going to talk mathematically about why it never touches that line as well. You can kind of see visually why it never touches the line, but we're going to talk about why mathematically it never touches the line. Okay, now a vertical asymptote, which is an up and down line. Oh, that's the eraser, I don't want that. I'll write this out. Is always x equals a number. And it's always, in fact, going to be x equals the non-permissible. Well, actually, no, that's not true. I shouldn't say that. Well, yeah, it is. It's always x equals a non-permissible, but it's not necessarily x equals a non-permissible. We'll talk about that too. Okay? If there is a vertical asymptote, it will be a non-permissible value, but not all non-permissible values result in vertical asymptotes. Okay? I hope I have an example of that in here. Do I? If I don't, then I've got to show you one for sure. No, I don't. Okay, we're going to do another one. We're going to do another example. I'm going to do one off to the side. We're going to do another example in a second, because I got to show you what it would look like if you have a non-permissible value that does not result in an asymptote. More on that later. If you have a horizontal asymptote, it will always be y equals a number. Okay, and in fact, in this course, it's always y equals 0. The x-axis is always the horizontal asymptote. If you take, well, actually, that's not true. But I'm not going to give you any examples. The example that I'll show you in a moment will have a horizontal asymptote of 1. But I won't ask you about that. I just want to show you where you can see an example where you don't get, in fact, a horizontal asymptote. Actually, no, never mind. It'll also have a horizontal asymptote of 0. I'm thinking ahead. I'm thinking 2 steps ahead. I obviously haven't been in the swing of things for a week and a half. That's my problem. Okay, so in this course, yeah, the horizontal asymptote will always be the x-axis. Okay, but if you take calculus, you'll get horizontal asymptotes that could be other values as well. Okay, all right, so if we look at f of x was x. Okay, where is that function undefined? Think of the domain. If you have y equals f of x, or y equals x, what's the domain of y equals x? Yeah. Yeah. What's the domain? It's the line. Yeah, x equals the reals, right? So the domain is x is an element of the reals. So where is this going to be undefined? It's undefined where there's like a break in the graph. Where's there a break in that graph? Nowhere, right? If the domain is everywhere, then there's no break in the graph. So where is the function undefined? Nowhere. Okay, now, what happens as x approaches infinity? What happens to the function? So this function, by the way, looks like this. So as x is approaching infinity, what's happening to the y values? They are getting larger and larger and larger and larger and larger. So they are also approaching infinity. Okay, so as x gets bigger and bigger and bigger and bigger and bigger, so does y. Okay, so as x approaches infinity, y also approaches infinity. Okay? What about as x approaches negative infinity? What's happening to y? As x goes this way, towards the left, what's happening to the y values? Yeah. They're decreasing. Yeah, they're getting smaller and smaller and smaller and smaller. So they are approaching negative infinity. Okay, does that make sense? Okay, now, when we look at this guy, when f of x equals, when this is 1 over x, right? Y equals 1 over x. Okay? Where is this function undefined? Where does this function not have a value? Where does it not have a y value? Yeah. 0. Yeah. That's where we got this vertical line where there's like a break in the graph. Does that make sense? Yeah? Okay, so it's undefined when x equals 0. Okay? Now, as x approaches infinity, right? This graph looks like this. Whoops. Looks like this. Okay. As x approaches infinity, what's happening to the y values? What are they getting close to? The x-axis. What's the x value? Sorry, what's the y value at the x-axis? 0. Yeah. Now, why does that happen? Well, if you look at the function, it's y equals 1 over x. So as x gets larger, we're taking 1 and dividing it by an incredibly large number, right? Think 1 divided by a very large number. And in fact, it's a very large positive number. 1 divided by an incredibly large number, think 1 divided by 100. Okay, that's 0.01. 1 divided by 1,000, that's that's 0.001. 1 divided by 10,000, that's 0.0001. Yeah. Exactly. Yeah, it's never going to be 0 because you're always taking 1 and dividing it by a number, so it's never going to be 0. But because you're dividing it by a larger and larger and larger and larger number, 1 divided by incredibly large number, by incredibly large positive number, is always, if you're approaching, as x approaches infinity, is going to be very close to 0, but on the positive side. Okay? Now, as x approaches negative infinity, as x is approaching negative infinity, here's negative infinity, what's happening to the y values? What are they approaching? Y is going like this. What are they getting close to? Here's the graph. It's going like this, or you can see here, y is going like this. There's the red line there. What's it getting close to on the graph? Yeah. Yeah, the x-axis, slightly below the x-axis, but the x-axis, right? That's a y value, again, of 0, okay? So again, y approaches 0. And why does that happen? Because as x approaches negative infinity, now we're taking 1 and dividing it by a very large negative number. Well, again, 1 divided by negative 100 is negative 0.01. 1 divided by negative 1,000 is negative 2 zeros, right? Negative 0.001. 1 divided by negative 10,000 is negative 0.0001. So you get something that's very, very close to 0, but on the negative side, which is why this line is just below 0, but again, close to 0. Okay? And because y approaches 0 as x approaches infinity, this becomes a horizontal asymptote, right? Because the y values are both approaching 0. Okay? So this y equals 0 is a horizontal asymptote. Now, what I'd also like to do for this y equals 1 over x is also take a look at what happens when we look at x approaching 0, because that's where we have this undefined value. Okay, so let's look at that graphically. And that's also very important to understand what happens at the vertical asymptote. And if you guys ever decide to take any mathematics beyond 30-1, you'll thank me for this, because this is basically all you're going to do is look at what happens here on a graph, right? This is what we're looking at right now is something called limits. What I'd like to do is look at what's happening as x approaches 0 from the right, okay? Okay, as x is approaching 0 from the right, what's happening to y? What's its approaching? What is it approaching? Yeah. Okay, well, it's going up and up and up and up. As y goes up and up and up, what's the maximum that y can be all the way up into the sky? Infinity, yeah. So as x gets closer and closer to 0, y is getting closer and closer and closer to infinity. Okay? Y is getting closer to infinity because as x gets closer, y is shooting upwards. Okay? Now, as x approaches 0 from the left, what does y do? Yeah. It approaches negative infinity because it shoots downwards. Exactly. Right? This is negative infinity. So y is approaching negative infinity. Okay? Now, why does this happen? Because as x is approaching 0, from the right, on the right side, x is still positive. So we're taking 1 and dividing it by a very small, what happened there? Shoot. Small, I'll stick in positive number. Okay? When you take 1 and divide it by an incredibly small number, you're going to get something enormous. Okay? So that's why y shoots upwards. As x approaches 0 from the left, I'm taking 1 and dividing it by an incredibly small negative number. So the magnitude of my number is also going to be enormous, but now it's going to be negative. Okay, so the reason here is that I'm going 1 divided by a very small negative number. So again, 1 divided by an incredibly small number. If you take 1 divided by 1/millionth, for example, you get 1 million. That's enormous. Okay? If you take 1 divided by negative 1/millionth, you get negative 1 million. The magnitude is still very large, right? The magnitude of negative 1 million is 1 million, but now it's negative, so it's going to shoot downwards. Okay, and that is why you get this divergence. Because you get this divergence in the graph, okay, we know that you cannot have a y value at x equals 0. And that's basically why we have this non-permissible value. Okay? Questions on that? No? Okay. Now, I do want to go on a slight tangent here because, as I sort of hinted at before, not all non-permissible values result in a vertical asymptote. Okay, so I want to show you what that looks like. Okay, so for example, oh, I missed something before. We'll go back to that in a sec. If we look at this, hold on. Yeah, let's do this. Whoops, no. Something like that. Okay. What are the non-permissible values here? If this was a rational expression, yeah. Yeah, so the non-permissible values would be x cannot equal 1/2, and anything else? Yeah, 0, right. Okay, could this be simplified? Can it be simplified? Yeah, sure. This can be simplified. If we simplify it, right? We can cross these out. We get y equals 1 over x, which is exactly what we saw before. So what is this going to look like? Well, it is going to look like what we saw before. With one exception. When x equals 1/2, y equals 1 over 1/2, which is 2. Okay, now x can't equal 1/2, which means y can't equal 2. So what we actually get is the point 1/2, 2 is a hole. It's a hole in the graph, and it looks like this. So here's 1/2, 2, and we have a little hole there. It looks like that. Okay, so if one of the non-permissible values actually simplifies out, you may not get a vertical asymptote there, but it will be a hole in the graph. Does that make sense? Okay, now I did miss something on the previous page, so I'd like to just go back before I forget and talk about this, the intersection points of the two graphs. Well, the intersection points are here and here. Okay, those intersection points have special names. So in this scenario, the intersection points are the points -1, -1, and 1, 1. Okay? The intersection points of reciprocal functions are called invariant points. And they always occur when y equals 1, or -1, I should say, actually. Okay, so they always occur when y equals 1 or -1. All right. Let's do another example. Do you guys have this on in your notes? You don't have the graph, but do you have the example? I don't know why. Mr. Ma copied all of the notes. He copied my notes for me, but he copied different notes to what I had. Anyway, I wasn't here because I was quarantined. All right, but you have this f of x equals 3x minus 9. Yeah? Okay, that's okay. The graph piece isn't actually that important. Okay. All right, so the goal with this, by the way, is not to have to make a table of values every single time, because that's a serious pain in the butt, right? That takes a really long time. So we want to be able to kind of become more efficient at this. And that's what we're going to kind of talk about, How do we become more efficient at this? Okay, and really what we'd like to be able to do is look at the original function, the polynomial function, and be able to come up with the reciprocal function from that, because we're really good at graphing linear and quadratic functions at this point, hopefully. Okay? All right, so determine the reciprocal function for f of x equals 3x minus 9. Well, if y equals 3x minus 9, then 1 over f of x, we're going to get y equals 1 over 3x minus 9. Okay? Now, graph f of x and its reciprocal and label any intersection points. Okay, well, we should know how to graph y equals 3x minus 9. This is a linear function, so we can look at the y-intercept, which is negative 9, and the slope, which is 3, so rise over 1 is 3 over 1. When we're looking at y equals the 1 over 3x minus 9, it may be worthwhile to actually factor this, because that will give us our non-permissible value, and that's going to become really important when we are graphing these things, okay? So I would actually factor this, and we can take out a common factor of 3, GCF of 3, right? Okay. Now, what is the non-permissible value there? When we factor that, what can we see the non-permissible value being? Yeah. Positive 3, yeah. And it doesn't cancel with anything in the numerator, so we're not going to get a whole. That means we're going to have a vertical asymptote there. Okay, we're going to have a vertical asymptote at x equals negative 3. So what we can tell from here is we're going to get a vertical asymptote at x equals negative 3, and we will also have a horizontal asymptote of the x-axis of y equals 0. Okay, so that can set us up to start. Those are a couple of things that are going to become important as we start to graph these things, the horizontal and the vertical asymptote. Okay, now I would graph this, the linear function. Okay, so you don't always have to graph the linear function if it's not asked for, or the quadratic, but it's helpful. So we've got this y equals 3x minus 9, so I'm going to start at negative 9. 6, 8, 9, there's negative 9. And I've got to go up 3, right 1 for my slope. So up 3, right 1, up 3, right 1, up 3, right 1. We can see that that's where the linear function equals 0, where x equals 3. Okay, and that's my linear function. That's a very bad straight line. Anyway. Okay, now what I'm going to do next is this. To get my reciprocal function, I am going to use dotted lines to mark in my asymptotes. So my vertical asymptote is over here. Not a solid line, because remember, these are not lines on the graph. Here's my horizontal asymptote. Okay, now my invariant points are when y equals 1 and y equals negative 1. So those should be the intersection points. Okay, so I'm going to do this in red maybe. So I have an intersection point here and an intersection point here. And then I know that I'm going to have a vertical asymptote that's going to get very, very close here, and a horizontal asymptote that's going to get very, very close here. And I'm going to use that to guide my graph. Okay? And on the negative side, again, here's my invariant point. My vertical asymptote is going to get close to that dotted line, and again, close to the dotted line for the horizontal as well. There's my reciprocal function. Okay. Now, if you're not asked for the original function, it's helpful to draw it in anyway, but make sure to draw it dotted because that's not what you're asked for. Okay. Often you'll be asked for both, though. Okay. All right. Now, find the equation of any vertical or horizontal asymptotes of the reciprocal. So we actually just did that. I didn't remember that was asked for, but there we go. And the reason why I did that is because this is part of my process, right? So when I'm graphing, I do this anyway. I may not actually explicitly write it out, but I would draw it on the graph. So this can just go down here. Okay? Discuss the behavior of the reciprocals as it nears the asymptotes. Okay, so as x approaches infinity, y is, and basically what we want to do, discuss the behavior of the reciprocal as it approaches the asymptotes. When you do this, when you're asked to discuss the behavior as it nears the reciprocal, here's what you want to do. You want to describe four things. Number one, what happens as x approaches infinity? What happens as x approaches negative infinity? Those are two. Okay? And then also, what happens as x approaches the asymptote from the right and the left? The vertical asymptote, that is, right? The undefined value of x. From the right. And then what happens as x approaches 3 from the left? Yes? You have a question? No, okay. Okay, so as x is getting close to infinity, right? As x gets close to infinity, what's happening to the function? What's it getting close to? Yeah, 0. Yeah, it's getting really close to the x-axis. The x-axis has a y value of 0. What about negative infinity? When x gets close to or approaches negative infinity, what's the function getting close to? 0 again. Yeah. So that's two of them. And if you have a horizontal asymptote, which in most cases you will, this will always be the case. In this course anyway, because you won't have any other horizontal asymptotes other than 0. Okay? When you get into higher levels, you will see other values like 1 or 2 or 10 or whatever, but not in this course. Okay? Now, what happens when x approaches 3 from the right? When x approaches 3 from the right, what's happening to the function? It's approaching infinity. Yeah. And what happens as x approaches 3 from the left? Approaches negative infinity. Yeah. Now, this is not always the case. Okay. Sometimes these are reversed. Sometimes they both approach infinity. Sometimes they both approach negative infinity. Okay, and we'll see examples of that as well. All right. You know what, the other thing that we should do, I know I didn't explicitly ask for this, but we drew these on the graph. I'd like to also, just before we move on, talk about how to find the coordinates of the invariant points. Okay, because that's also important. Okay? Now, the invariant points happen where y equals 1 and y equals -1. Okay? So what you need to do is you need to plug in okay? You need to plug in y equals 1 for either the original function or the reciprocal function, and then solve for x. Okay? Now, why do you think actually the invariant points happen at 1 and -1? Does anyone know why? What's the reciprocal of 1? What's the reciprocal of 1? If you wrote 1 as a fraction, what would it be? 1 over 1. What's the reciprocal of that? 1 over 1, yeah. If you wrote -1 as a fraction, what would it be? -1 over 1. If you take the reciprocal of that, it's 1 over -1. So that's where the two functions are going to equal each other. So that's why the invariant points happen there. Okay, now to find the invariant points, the coordinates, all you need to do is for one of these two functions, set y equal to 1 and set y equal to -1 and solve for x. You can plug 1 and -1 into either one. It's probably easier to plug it into the linear one than the reciprocal. Okay, so plug -1 and 1 in for y into either function and solve for x. Okay, so let's do the linear. So if y equals 1, we get 1 equals 3x minus 9. So I'd get 10 equals 3x. So then x equals 10 over 3. Okay, so one invariant point is 10 over 3, 1. And that's this guy right here, right? It's actually 3 1/3. So it's just over 3 for the x value anyway. And then when y equals -1, we have -1 equals 3x minus 9. So we're going to have 8 equals 3x, and we get 8 over 3 equals x. So the second invariant point would be 8 over 3, -1. So that's like 2 2/3, which is right below 3, and -1. And that's the other one. Okay? So that's how you would find the exact coordinates of the invariant points. Okay? All right. All right. Now, what do you guys have in your notes on this next page? Actually, I think I have.
All the questions are listed.
Just nothing else.
Yeah.
The questions? Oh, I see. Okay, just not the graphs. Okay, that's okay. You don't actually have to have too much for the graphs because you really just have to draw in the asymptotes. Yeah. Back? Yeah, absolutely. Yeah. There you go. Either. There we go. Okay, I think we'll do one more, and then we'll stop. Okay, so this next guy is a quadratic. All right, so determine the reciprocal function of f of x equals x squared plus x minus 6. Okay, so we've got this function y equals x squared plus x minus 6, and then the reciprocal would be 1 over f of x, which is y equals 1 over x squared plus 6, plus x rather, minus 6. Okay, now always, always, always factor, because when we are graphing these reciprocal functions, we need to know where is this function undefined, because just like the linear function, we're going to have vertical asymptotes at those spots. Okay, so we would want to write this instead as, okay, we need it to multiply to negative 6 and add to 1. So that's x plus 3 times x minus 2. Okay? All right, now, where are the x and the y-intercepts of the reciprocal? Okay, well, to get the x and the y-intercepts, we have to remember that the x-intercept occurs when y equals 0, and the y-intercept occurs when x equals 0. Okay, so the x-intercept, y equals 0. So we can plug in a 0 for y and try and solve. Okay, now think about this. If you were solving a rational equation here, like if you treated this as a rational equation, you would multiply by the LCD, which is x plus 3 times x minus 2. If you multiplied both sides by x minus 3, x plus 3 times x minus 2, you'd get 1 on this side and 0 on this side, because 0 times this denominator is still 0. You get 0 equals 1. Is that possible? No. What that means is that there is no y-intercept. This is never true. Okay? This thing never touches the y-axis, never crosses the y-axis. Or sorry, no, x-axis. Never mind. No x-intercept, my bad. Y never equals 0. No x-intercept. Because y never equals 0. Right? We can't find an x value where this is true. Okay? On the other hand, for the y-intercept, x equals 0. So y is going to be 1 over 0 plus 3 times 0 minus 2. And that is 1 over 3 times negative 2, which is 1 over negative 6. Okay, so the y-intercept is 1 over negative 6, or negative 1/6. Okay. Graph f of x and its reciprocal, label any intersection points. Okay, well, there's a couple of things we got to do here. If we're going to graph f of x is a quadratic function. And to graph f of x by hand, we have to have that in vertex form, right? It's in standard form right now. So we've got to go and complete the square to get that into vertex form. So we've got to do that first. And then we can go about graphing f of x plus the reciprocal function. Okay, so we're going to do that first. Okay, so we've got y equals x squared plus x minus 6. Okay, so we need to first, to complete the square, we need to, the a value is 1, so that's nice. We need to take half the coefficient of x. Coefficient of x is 1, so half of that is a half, and square it. Half squared is a quarter, so that's 0.25. So we're going to take x squared plus x plus 0.25 minus 0.25 minus 6. Okay, and then we can take this out. Minus 0.25 minus 6. Okay, and then this becomes x plus a half squared and then minus 0.62 or 0.25 rather. Okay, so basically it looks like y equals x squared, but the vertex, instead of being at 0, 0, is at negative a half, negative 6.25. Okay, so well, let's see. 1, 2, 3, 4, 5, 6. So the vertex is like right there. Okay, and then remember, like the next points are negative 1, 1, 1, 1. So I'm going to go 1, 1, or negative 1, 1 rather, and then 1, 1. And then the next point would be negative 2, 4. So negative 2, 4, 1, 2, 3, 4, and 2, 4. Okay, now the other thing that I can do here when I'm graphing is I also know where the x-intercepts are of this graph because we factored when we did the reciprocal function, right? And it factors into this. So I'm going to have an x-intercept at negative 3 and 2. So I might put those points in as well. Negative 3 is right here, and 2 is right there. And maybe I'll just use that to guide me. Okay. All right, so there's f of x. Now to get 1 over f of x, I need to put in a couple of things. I'm going to put in my asymptotes. So I know I have a vertical asymptote at the two undefined values, which are negative 3 and 2. Because when I factored, that's where x cannot equal 0. Okay, so from this factored version, actually, I know that I'm going to have vertical asymptotes at x equals negative 3 and 2. And my horizontal asymptote is y equals 0. So I'm going to put those in to guide me, to guide myself, I should say. I'm not like speaking proper English today. Okay, so here we go. There's one, there's the other. Okay, and then y equals 0 is the next one. Okay. And I am going to My intersection points are going to be where y equals 1 and where y equals -1. So I'm going to have an intersection point here, 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 and here. I didn't really draw these all that well, but there we go. Should have done a better job at drawing f of x because it looks like it's right on the asymptote, but you kind of get the idea. Okay. Now the other really important point is the point that's going to go up here. Okay. This is the minimum value of this function. Yes? That means that this point up here should be 1 over that minimum. So if this is the point, -0.5, -6.25, this point over here should be -0.5, 1 over -6.25, which is very close to 0, but not touching 0. Okay, it's almost like it, well, for this section of the graph between these two vertical asymptotes, that is like a maximum point. Okay? And now this is going to go like that. So those sort of 3 points will guide your graph. Right? So it's like this maximum point up here plus those 2 invariant points will guide the rest of it. Okay? And then for the other 2 sides, this invariant point is one point that you must have on there. And then these go up like that. Okay? Now we are also asked to label the invariant points, which means we need to actually write out the coordinates. Okay, so pay attention to that. Label any intersection points. To do that, we actually have to solve those equations, right? Set one of the functions, probably the easier one is the original function, equal to 1 and equal to -1, and then solve. Okay, so that's what we're going to do next. I'm going to do that here. We'll do this actually right here. So the non-permissible values of the reciprocal. So x cannot equal -3 and 2. The horizontal asymptote is y equals 0. The vertical asymptote, we did this above anyway, is x equals -3 and x equals 2. Now I have some space to work on the invariant points. Okay, so invariant points. There we go. Okay, so my invariant points, we're going to set the original function or its reciprocal equal to 1 and -1. So 1 equals x squared plus x minus 6. Okay, now to solve that, I need to equate to 0. So I'm going to do that. Okay, and then the only way to solve this, it doesn't factor. So what do I need to do? Quadratic formula. Yeah. Okay, so I've got to go x equals minus b minus 1 plus or minus the square root of b squared, 1 squared, minus 4 times 1 times 7 over 2 times 1. And that is -1 plus or minus root 1, oh, that should be a minus, plus 28, 29 over 2. And that is, I don't know. I need a calculator. One of them is 2.2, or negative 3.2. Okay, so the 2 points are 1 and 2.2, and 1 and negative 3.2. That's 2 of them. And then the other invariant points we have to set equal to negative 1. And then I think we're going to have to use quadratic formula again. Minus 5. Right? So again, yeah, doesn't factor. Okay, so negative 1 plus or minus the square root of 1 squared minus 4 times 1 times negative 5, all over 2 times 1. That's a bit annoying. So that's negative 1 plus or minus root 1 plus 20, 21 over 2. $1.8 or negative 2.8. Okay, so these 2 points are negative 1, 1.8, or negative 1, negative 2.8. Yeah? So we got to label those. So this would be the 1, 3.2. This would be the 1, 2.8. This would be the 1, negative 1.8. And this would be, no, negative 1, the 1, negative 2.2. There they are. Yeah. Okay, I think we'll leave it at there for today. We'll call it a day. It's tedious. It's a lot of steps, but it's not, you know, each one is not terribly hard, there are not too many curveballs that we can throw you here, right? If you can do the linear one, if you can do the quadratic one, if you practice it a few times, then you'll kind of have it, hopefully.